All right, welcome to the November Bridge Builder Seminar. We're so happy to have you here. This is our last seminar for 2025, so it's a blessing to have so many people show up. Thank you. Just a quick announcement about next year. We're planning 2026. So I don't have anything to announce just yet, because we're going to make some changes that I won't announce just yet because I will be wrong by the time we get to 2026.
Okay.
But we are going to do some things different, and I think you'll enjoy the way we're going to do it in the future. So I'd like Bob to open us up in prayer. So if we could go to prayer right now. Thank you.
Before we do that, I'd like to read a passage from God's Word. This is Proverbs chapter 8. Verses 12 through 31. The thing about Proverbs is written, there's 7 sections with the Proverbs. This is the first section. And this ends, what I'm going to read ends the first section, or close to the end of the section. But it touches on God, how he expresses how wisdom personified, expressing God's creation poetically. So, listen to this. I, wisdom, dwell with prudence, and I find knowledge and discretion. The fear of the Lord is to hate evil, pride, arrogance, and the evil way, and the perverted mouth I hate. Counsel is mine, and sound wisdom. I am understanding. Power is mine. By me kings reign, and rulers decree justice. By me princes rule, and nobles, all who rule rightly. I love those who love me, and those who diligently seek me will find me. Riches and honor are with me, enduring wealth and righteousness. My fruit is better than gold, even pure gold, and my yield better than choicest silver. I walk in the way of righteousness, in the midst of the paths of justice, to endow those who love me with wealth, that I may fill their treasuries. The Lord possessed me at the beginning of his way, before his works of old. From everlasting I was established, from the beginning, from the earliest times of the earth. When there were no depths, I was brought forth, when there were no springs abounding with water, before the mountains were settled. Before the hills I was brought forth, while he had not yet made the earth and the fields, nor the first dust of the world. When he established the heavens, I was there, when he inscribed a circle on the face of the deep. When he made the firm skies above, and the springs of the deep became fixed. When he set for the sea its boundary, so that the water would not transgress his command. When he marked out the foundations of the earth, then I was beside him as a master workman. I was daily his delight, rejoicing always before him, rejoicing in the world, his earth, and having my delight in the sons of men. Let's pray. Our Father, how many are your works, and wisdom you have made them all. The earth is full of your created works, and we marvel. Lord, we marvel at the starry heavens above and the moral conscience within. We marvel when we see a bird fly through the air, and when we see a baby born. Lord, our mouths are closed. Our hearts skip a beat when we think of all that you did, your creative powers, and even most of all, you have caused us to be able to see and realize that you are God and you did all these things. Because for many of us here, there was a time when we did not recognize you. Thank you, Lord, for bringing us to yourself. We ask that you bless our time today, and the speakers who will present. We ask, Lord, you give them everything they need. And draw us, Lord, to yourself. Let us see your amazing wisdom and what you did for our marvel, and that we might trust you for the things we can't see. In Christ's name we pray. Amen.
Amen. Thank you, Bob. All right. Our first speaker today is Tom Hunnell. Tom has a Bachelor of Science in Aerospace Engineering from Purdue University. His career started at General Dynamics Advanced Design Group and subsequently received a Master's of Science degree in electrical engineering at the University of Texas at Arlington. He finished his career at General Dynamics Lockheed, working on the electrical power systems of the F-22 and the F-35. Tom retired in 2021 and now is speaking. So please welcome Tom Hunnell.
Thanks, David. I wanted to talk just a little bit about this slide to start off with, and I wanted to point out something else too. Notice this is the pointer that David provided, and this is the one I brought from home. So I kind of look at some of the presentations that have been made as they have a Michelin rating of like 3 stars, 4 stars, whatever that is. Well, my presentation is kind of like, would you like fries with that? So just kind of keep that in mind. This picture was actually taken at the Cowtown Air Show in 2024, last year. And I thought that was a pretty good shot, and I really liked it. I've never worked on an F-18, so I must confess that. But I thought this was really neat that you can see these airplanes flying in formation. And one of the things to kind of note, and this kind of relates back to Top Gun, you see how some of these F-18s have an empty seat in the back? That's so they can carry an observer on some of the flights. So when you ever see like pictures of a guy flying with the Blue Angels, he's typically in the back. They'd like to show him because he's getting smashed in the seat and very uncomfortable. But that's why they have some of those airplanes with 2 seats. Okay, let's see if we can get going here. You know, it's kind of like when you look at birds flying, you think it is a miracle. And to me it is. And then I was talking to David the other day about this, and I said, you know, if birds hadn't flown, I'm not sure man would have figured out how to do it. So it's kind of like when you think about a lot of these things that man does, they're basically copied from stuff God has already done. And I thought this Bible verse was pretty applicable, and I think, in fact, pretty much both of the presentations you're going to see today, I'm day 5, and John, you're going to be day 6, right? So it's kind of funny how things tie together. But the verse is Genesis 1, 20, 21. And God said, let the water swarm with swarms of living creatures. Let the birds fly above the earth across the expanse of the heavens. So God created great sea creatures and every living creature that moves, with which the waters swarm according to their kind, and every winged bird according to its kind. And God saw that it was good. Well, I believe it was good. In fact, the way I see things, birds are incredible and very good. I know he reserved the very good for humans, but when I'm looking at a bird, it's just like absolutely amazing. And I've got to keep up. Now, another thing to notice is, you know, in some of these presentations, we've talked about AI and all that kind of stuff. Well, here's my notes on 3x5 cards. That tells you where I am. And as David mentioned, I worked at General Dynamics and Lockheed for 40 years. And what's funny to think about is when you look at that time, so much has happened. When I first started working there, we had drafting boards, and one of the vice presidents of engineering predicted that one day everyone would have a computer on their desktop. And we laughed, because we thought that's a silly thing. Well, look who's laughing now. Okay, so let's see. You know, it's a lot of times we often think birds fly. And that's unique. Birds fly, sure. That's a pretty simple statement. But I think when we actually look at birds flying, I think we should look at them and say they were created to fly. Because God made them. They're incredible. And we learned how to fly from them, and we're actually still learning. Because some of the systems in birds are far more complex than what we can do today with the technology that we have. And we'll talk a little bit about that. Okay, let's see. Let's go to the next slide. Okay, this is kind of a quick summary of the things that we're going to talk about today. And we're going to kind of just hit the very high points. This is just like zipping through these topics. You could spend probably, you know, many, many lectures in a university going over any one of these topics. But we're going to try to hit them really quick just to kind of give a leveling class, if you will. I wanted to talk a little bit about the first flight, first manned flight. And believe it or not, you know, when you're raised in America, you're taught Wright brothers flew, and that was it. But there's actually controversy around that, and we'll talk about that in a little bit. But again, in our American mindset, we want to think the Wright brothers were first, that's end of story. Then we're going to kind of hit the basics. And what's funny about this is a lot of these things we're going to talk about, you already know. Now, the aerospace engineering and that kind of thing, what they do is they like to take things that people know and kind of organize them in different ways so you can kind of see them in a little different light, maybe a little more structured, a little more engineering-ish, if you will. Then we're going to talk about airfoils and wings, and that's kind of a concept that's a little bit misunderstood. A lot of times people interchange those words, but typically, in a technical standpoint, an airfoil is a 2D element and a wing is a 3D type thing. And there's differences in how they act. So we'll talk a little bit about that. Then I wanted to go to the design process, and I think last session David said something about get ready to roll up your sleeves. We're gonna bend metal and pound stuff in place. This is kind of, well, tongue-in-cheek. We're going to do a little bit of that, very small. And then we're going to talk about an example in the preliminary design process and how that might look, kind of some of the factors that you have to consider. And then to kind of close this thing out, we'll go back to birds to look at kind of tie in what we've talked about from a technical aspect prior and to how birds work. So that's kind of the agenda for today. All right. First in flight, the controversy. Here it is. Here in America, we all think Wright brothers flew, Kitty Hawk, all that good stuff. Well, I ride bikes with a lady that's from Brazil, and she said, if you are going to do a presentation on aircraft design, you have to talk about Santos Dumont, because there's parts of the world that believe he was actually the first person to fly, and they have reasons. And what's kind of cool is in this picture, it kind of shows the different reasons. The idea is if you live in Brazil, the Wright brothers cheated. You see this? That's a rail that they actually launched their airplane from. And they said, that's part of that was required for takeoff, and it didn't stay with the airplane. So it doesn't work. You didn't really fly first. The other thing is, if you look at how many people were here, there's like Orville, I can't remember if he was flying or watching, Wilbur, a guy taking a picture, and maybe a couple other folks. So it wasn't well attended, and so they're like, well, they could have faked it. Does that sound familiar? Moon landing, all that kind of stuff? Well, if you look at Santos Dumont, he flew, I think this was in France actually, but you can see that incredible number of people here. Here's a guy taking pictures, documenting it. What's interesting is, here he is flying the airplane, you actually stand up to fly it. So it's kind of different. We don't really think of that, standing up to fly an airplane is kind of odd. But if you also look, he's got wheels on that airplane, so everything it needed to take off was with the aircraft. And so that's why they say he was first to fly. Now, my opinion, I'm American, I'm going to go with the Wright brothers, and you can't underestimate you can't overstate how complicated this task was to get this airplane to fly. And what's interesting about that is it looks complicated in the big picture, and there's a lot of things that they were really smart to figure out. But the basics of that aircraft were really incredibly simple. They were using bicycle parts, things that you'd find in an umbrella, kind of umbrella technology rolled into this aircraft. And as part of this presentation, I looked on ChatGPT and I thought, why did the Wright brothers succeed and so many other people that were trying to fly fail? Because there were people that were heavily funded. The Wright brothers were basically doing this in their garage. And the thing that ChatGPT said was, the reason they succeeded was they took a logical approach to flight. They questioned all the available data. They actually built their own wind tunnels to get airfoil data in order to design their wing better. They also built their own engine in their own shop. They had a machine guy who built it for them, 12 horsepower. They flew on 12 horsepower. And so the big thing, though, the biggest reason was they focused on control. And that's what we're going to talk a lot about today. There's something called a neutral point on an aircraft that we'll go into a little bit. They were very concerned about that. They were very concerned about where the center of gravity was. And we'll talk about kind of how those things play together. But that was their main concern. So they succeeded, others failed. So that tells me control is very important. Okay, let's go into like the basics. Here's the funny thing. A lot of this stuff you already know. We'll kind of amplify a few things, but if you've ever taken your hand and stuck it out a car window driving down the road, you know that if you hold your hand like this, there's not really that much force on it. But if you tip your hand up, give it an angle of attack, now the story changes. You start generating lift and you can kind of feel it getting pushed back a little bit. Well, if you take it to the extreme and you crank your hand back like that, you know there's a lot of force on it. The other thing is depending on how fast you're going, those forces can change a lot. If you're driving in a car going 30 miles an hour and you stick your hand out the window, I recommend doing this at night, because if you do it during the daytime, people look at you like you're a nut. Take it from me, I know that from firsthand experience. But if you're running 30 miles an hour and you start doing that, there's some force on it. But if you do it at 60, you're going to really feel it. And so now let's kind of tie that back. First of all, let's talk about air. We've talked about that a little bit already. We talked about how if we didn't have a magnetic field on Earth, the solar winds would carry the atmosphere away. So it's a miracle that we have an atmosphere that's as stable as it is, consistent, and dense. So I mean, it's really kind of amazing. The density of air is like a little less than 1/10 of a pound per cubic foot. So you got a cubic foot that's like this big, less than 1/10 of a pound. And it doesn't sound like a lot, but if you look at it a different way, if you take like a small bedroom, like 11 by 12 by 8, and if you could compress that air into like a block that you could carry, it'd weigh 81 pounds. So there's a lot more air than you think. You know, you always think air is just, it's just a little bit more than a vacuum. Well, there's actually a lot of density in that air, and that's very important when you're considering aerodynamics and forces on a wing. There's a thing called dynamic pressure that's key in flying. And the way it works is you take the density of the air and you square the velocity. So again, back to the example, your hand out the window. You're going 30 miles an hour, you've got a certain amount of force. When you go 60, the force doesn't double, it quadruples, because there's a square term. And then you take half of it, and that's just kind of the way the math works for that particular equation. That's called dynamic pressure, and sometimes you'll hear it referred to as Q. A lot of times when somebody's talking about an aircraft regime of flight, they'll talk about a high Q situation. That means it's going really fast. There's a lot of dynamic pressure. When you talk about aerodynamic forces, and again, this is where some of those engineering conventions start working in. And they kind of put a cloud of fog around some stuff that's actually fairly simple, because you already know it because you had your hand out the car window. So you've got lift, which is dynamic pressure times what they call a coefficient of lift times an area. So that brings those terms into like a force that you'd see. Now lift is always considered to be normal or 90 degrees to the velocity of the free stream air. Drag is the same kind of thing, where you've got dynamic pressure times a coefficient of drag times an area. And again, it's going to be parallel to the velocity of the wind that you see. There's also a moment that's generated, which causes the thing to want to pitch up or down. And that's typically referenced to the aerodynamic center. And the reason they pick an aerodynamic center is that's where the moment is going to be constant as the angle of attack of the airfoil changes. So you can kind of see here's angle of attack, or alpha. A lot of times they refer to things in letters in engineering. Okay, next thing I wanted to talk about, again, this is kind of where the Wright brothers ties back in. Wright brothers were very concerned about stability, and so that's kind of where we're going to focus. And the key thing to think about when you're talking about stability is typically you'll have two control surfaces on an airplane, and I just drew this as a conventional winged and aft tail. But when you combine those two lifting surfaces, you'll end up with something called a neutral point. And how they're combined is a little bit complicated, but it's basically kind of averaging the lift that those two surfaces are going to generate. Well, what happens is, if you have this neutral point back here, the center of gravity, if it's in front, it's stable, which stability sounds more complicated, but what it really means is you're going to point into the wind. So when you think about an arrow, just to go back to simple and things you already know, you've got the fins way back here, and you've got the CG, the center of gravity, way forward of that. So that tells you an arrow, if you shoot it off the bow, it's going to be incredibly stable, because the aerodynamic, the neutral point is way back where the fins are, and the center of gravity is way forward, like halfway down the shaft of the arrow. So it's going to be a very, very stable system. When you start putting a wing in front, it looks more complicated, but it's really not. It's the same exact thing. So the idea is that if you get a gust, you want to get a negative moment around your center of gravity. So again, you're flying into the wind. That's all it's saying. I think that's pretty much it on that. Again, it's one of those things where when you watch an arrow fly, you already know what's going on. Okay, trying to put this in a little bit of a pictorial way. This is kind of a classic thing that they love to show in engineering books. Is if you have a system that's stable, in other words, the CG's in front of the neutral point, just like an arrow, you kind of operate in this bowl where if you get hit with a gust, it might push you up here, but it's going to roll back down to a stable situation. If you're neutral, where you've got the neutral point, aerodynamic forces are centered right on the CG, you get something that looks like a flat surface where once you get it moving, it's going to keep moving until something else happens. If you're unstable, you end up with a surface that looks something like this, where the ball's sitting on top here. If you get even the tiniest disturbance, it's going to take off and run away on you. There's a saying in the model airplane world that an aircraft with the CG too far forward flies poorly. If the CG is too far aft, it flies once. So that's a relative. So if you fly model aircraft, get that CG forward and then pull it back as you've flown it a few times. Now, this I'm hoping nobody has had firsthand experience with, but unfortunately I have. I had a friend back in my college days who didn't have a lot of money, and we went on a road trip. We drove his car, and he didn't really have the money for good maintenance, and the alignment on that car was terrible. And if you've ever driven a car that's out of alignment terribly, it's very hard. What happens is you'll be driving down the road and you'll finally get it going straight. And so you've got to like I got this thing under control, and all of a sudden you hit a pebble or something on the road and it wants to jerk over 3 or 4 feet. So you're like, oh my gosh, I got to get back. So it's like you're constantly fighting this car. And that's kind of what goes on with this unstable condition. Anything that happens is going to want to throw it off into the weeds, and you've got to fight it all the time. So 2 things are going to happen. Either your pilot's going to get worn out if he's trying to fly that thing, or he's not going to be able to do it. So it's kind of one of those things where if the pilot's not fast enough, that thing's going to depart, and you're going to end up with a bad situation. Airplane's going to fly once. Okay. So that was longitudinal stability. That's kind of the long ways of the airplane. Now we'll talk about roll. There's a way that you can increase stability and roll. And if you think back to the Wright brothers airplane, did you notice that their wing was like almost completely flat? It almost had a little bit of anhedral, they call it. There's dihedrals when the wing rolls up a little bit, anhedrals when it goes down. Their airplane was kind of in this situation where they had the center of gravity here and they had the neutral point that was kind of more or less on top of it. Now it was a biplane, so it's going to get a little bit higher based on that. But still, a lot of times when you hear the Wright brothers airplane described, they'll talk about them as unstable. And actually, some people say it was unstable in pitch. I'm not so sure that's really true, but I think definitely in roll it was, because it had the anhedral and it would have been difficult to fly. One thing you can do to kind of get the airplane more stable, and a lot of times if you've looked at model airplanes and that kind of thing, you'll see that they slope the wing up. What's helpful about that from a stability standpoint is if you move that wing up, the neutral point is going to go up with it. And now you get kind of like a pendulum effect, where you can think of the lift being centered around this neutral point, but the weight is down here. So you get more of a stabilizing thing, kind of like holding a pendulum. It wants to kind of go down. Very similar thing. There's some aerodynamic effects that play into that too, but I'm not going to go there today. So again, stability, incredibly important. CG emplacement, incredibly important. And figuring out where your neutral point really is. All that is really, really important to fly an airplane. Okay, let's talk a little bit about aerodynamics. And this is kind of when people talk about airplanes, they always think, wings, all that stuff's really cool. So some of the terms that are used is an airfoil, typically, like we talked about already, it's a 2D kind of thing. Usually it is based on an infinite wing, which what that means is that wing just goes out to infinity and there's no kind of trickle around the tips. So there's no vortices around the tips. It's just You're only looking at the airfoil and that's it. That's done in order to kind of simplify some of the analysis and where you can compare wind tunnel data from one airfoil versus another. This is a lot of what the Wright brothers did. They have a museum in Dayton. You know, everybody likes to go to the big Air Force Museum, but there's another one there that I think is much, much smaller, but it's really interesting. And it's called the Huffman Prairie Field, or Interpretive Center, or something like that. If you get a chance to go to that museum, it's not going to be crowded, and it's very cool. And it talks about some of the stuff the Wright brothers did. I think they've got either a mock-up or the actual wind tunnel that they used to do a lot of their airfoil testing, and it's fascinating. Those guys were geniuses, and you just can't say enough about them. But the 2D airfoil, you get that data from wind tunnels. Sometimes they'll do it analytically now, where the computers are getting strong enough that things like that can happen. Typically, the viscous effects are kind of minimized, where you're kind of like, well, we're not really going to worry too much about that. One thing about that is when you get the airfoil data, you'll see slope something like this. This is coefficient of lift for drag, so that's kind of an efficiency rating, if you will. If you just take an airfoil and you test it, you can get coefficients of lift to drag of like in the 100, 150 ranges, incredibly big numbers, which basically means if the airplane was a foot high and you flew it, it would go 150 feet before it dropped. So I mean, that's crazy. What happens though is when you go to a three-dimensional wing where you're trying to make something that actually works, it takes the finite length of the wing into account. So what ends up happening is, instead of just getting this nice smooth flow over the wing that meets at the trailing edge, you get these really big vortices that form around the tips, because there's a high pressure region on the bottom, low pressure region on the top, and of course stuff wants to go to a stable condition where those pressures want to balance out. And the wingtip is the only place they can do it. So you get these really, really big vortices around there. I don't know if you guys have seen like an airplane in an air show, where if it's a humid day, sometimes when they're pulling a lot of G's, you'll see a vapor trail form around the wingtip that kind of follows the airplane. Well, this is the effect that you're seeing. This air gets moving really fast around that vortice, and it causes a low pressure region. And so the humidity in the air basically falls out of solution, and it becomes like a liquid, you know, just droplets. And so you can see those droplets. So when you see a vortice coming off of a wing or something, doesn't necessarily mean it's on fire. You know, it can mean that it's really working. Now, when you take an airfoil, one thing that can happen is if you crank the angle of attack too high, you can actually detach the flow. And you see these turbulence breaking off the back where, you know, bad things are happening. And that's a little bit of what you're seeing here. This is kind of an analytical solution, so it doesn't really reflect the true turbulent nature of the flow. In reality, this curve would probably roll around a lot quicker than that. And that's, you know, again, you have your hand out the window, you turn it like this, you can just feel how hard that is and how hard the air's working to get around your hand. And that's exactly what you're seeing there. Now, when you take the same airfoil and you put it into a wing that's of a fixed length, now you start seeing this coefficient of lift versus drag get a lot lower. So, you know, typically on a real airplane, that's probably going to be in the 10, 15 to 1 kind of thing. So if you had the airplane a foot in the air, you pushed it forward, it'd go 10 to 15 feet in front of you, which kind of makes more sense based on, you know, when you're a kid and you throw an airplane, what you see. So one other quick note is when you're talking about airfoil type data, typically the L and the D in the subscripts in those coefficients are lowercase. When you go to a wing, you'll see them written as uppercase. So that's kind of one way, if you're looking at data, you can tell that it's different, if you ever have reason to do that. Okay, no really good presentation about airplanes is complete without some kind of reference to a spaghetti western. So here's mine. We've got the good, the bad, and the ugly. And pardon to my friend from Brazil, but I do think that aircraft is ugly, and I'm going to say it out loud. Okay, the good things, you want lift. And what you want is if you can make that span really, really large, those vortices aren't as big of a factor because you've got more lifting area before you see that flow around the tip. So what you want to do as an aerodynamicist is you want to make that wing as huge and long as you can. And think about gliders. You know, when you look at a glider, the wing's way out there, and that's because they're trying to get these really, really high L over D's, lift over drag, because they want that thing to glide for as far as it possibly can. Another thing that's great is thrust. In fact, I had a great boss at Lockheed, and one of his favorite sayings was, "Thrust covers a multitude of sins." So you can design the aircraft really, really bad, but if Pratt can come through and give you an engine that'll push it really hard, you're going to be all right. The bad things are weight, bad, hate it. Drag, and these two kind of go together, because the more weight you have, the harder the wing's going to have to work, and the bigger those tip vortices get, so you start ending up chasing your tail trying to get there. So drag can be wetted area. You want to keep that thing tight, really, really small. You get induced drag, that's vortices around the tips. Form drag, where if you got something that's big, fat, and ugly, it's gonna have more drag than something that's thin and beautiful. And then trim. So if you've got to move your tail around to keep the airplane stable or keep it from going to someplace you don't want to, that's going to cost you drag too. So you've got to take all those things into account. Also, any air you take on board, like let's say I've got an oil cooler and I want to get some flow through that so my oil doesn't get too hot. All that air that you're taking on board, you're slowing it down. When you change its momentum, airplane has to push harder to make it go. So you really, really hate to take on air. Again, this is my Brazilian friend. This airplane is actually, I don't know if you guys have seen this or not, but this is I think it's the F-32. It was the Boeing offering for the JSF contract. And I was working on F-22 at the time, and when this stuff finally went open where you could see what folks were doing, I didn't believe that was really the Boeing entry. I thought, oh my gosh, that thing, not necessarily the prettiest thing I've ever seen. But I did have a boss, and when he saw an airplane like that, he'd say, it's not ugly, it's brutishly aesthetic. So there you go, brutishly aesthetic. So I apologize, these are not ugly, they're brutishly aesthetic. Okay, now let's start getting into it. When you start designing an airplane, and we're kind of focusing in specifically on like control and that kind of thing, but there are so many things that play into it. And this is where aerospace becomes an art. You're going to get a set of requirements, and it could be from the government, it could be from somebody who wants to build a medevac airplane or something like that. But there's going to be a lot of things that come in. Max speed, payload, how much stuff does it need to hold? How far does it need to go? What's your max altitude? Because you might have to completely design a fuel system if your service ceiling is 12,000 feet versus 50,000 feet. The world's different when you start getting at those higher altitudes. So you've got to kind of think about that. There are also speed, subsonic versus supersonic. When you go supersonic, the whole world changes. I like to think of supersonic as if you imagine a busy street in New York and there's people that are walking this way and you need to go that way. If you just walk at a slow pace, people kind of see you coming and they get out of your way. But if you try to run through that crowd, it's a different thing. You're banging into people, knocking them over, all that kind of stuff. So a lot more turbulence, a lot more drag. That's kind of what supersonic is. The air just doesn't have a chance to get out of the way. And then you might have a bunch of avionics. Somebody might want to put some newfangled radar or some kind of comm system on there that's incredibly complex and takes a lot of power. Well, power's heat, blah, blah, blah. Again, you're chasing your tail. That happens a lot in working on airplanes. So those are the requirements. And then what happens is there's a group of people that are going to try to lay out airplanes. They might pick a Delta configuration, kind of a conventional thing, and a canard, and say, we're going to figure out which one of these is going to meet the requirements the best. Well, the way you do that is you've got to have really good guys that know how to do aero and performance, which is kind of like the drag and stability and those kind of things. You've got guys that are going to do a flight system. How big do my surfaces have to be? How quickly do they need to actuate? Am I going to make the airplane stable or unstable? All those kind of things are going to play in it. There's subsystems. Subsystem. There's structure, pretty obvious. We're going to run I-beams down the airplane wing and all that kind of stuff. There's propulsion. Those guys are going to work on the design of the inlet, the engine, all those kind of things. Mission systems, what avionics do I want? Do my radios have to be encrypted? Can I just, be out there and talk to anybody? What do I want to do? Reliability and maintainability, R&M, that's huge. If you build an airplane that can't be maintained, everybody's going to hate it. because it's going to be on the ground a lot. And then you kind of have the weight and balance guys. So what happens is people will come up and draw these configurations. They'll run them through these subsystems and say, okay, what do you guys think about this? Some of them they're going to love, some of them they're going to hate. And what has to happen is you have to have a really, really balanced approach to where everybody kind of has an equal statement in this, or you're going to end up with something that just doesn't work. Now, one thing that you'll see left off, this is kind of a pretty common slide. You'll see it written a bunch of different ways. But one thing a lot of people leave off is safety. And working at Lockheed, I will say that we, as a company, I never saw anything that I considered unsafe go out for flying. You know, there's stories out there about companies who took shortcuts when it comes to safety and that kind of thing. That didn't happen at Lockheed. There were too many guys that were too good. The test pilots were good. The engineers at Lockheed wouldn't let it happen. And you had a voice. If you, as an engineer, if you threw up the BS flag and said, this is not leaving the ground, people would listen to you. So I have a very, very healthy respect for Lockheed and the people that work there. And some of the things you heard about recently that happened wouldn't happen there. And the safety guys do something that's a little bit different, and they're going to say, hey, I'm okay with different, but you got to show me that that's going to be safe. The safety mindset, a lot of people think in that a lot of times you say, I'm going to show my thing works. Well, when you have a safety mindset, you don't show it works, you show it can't fail. And the two are completely different. Where if you've got some You know, I see one thing, when I was doing this presentation, I was thinking about AI, and it was like, man, have you ever seen anything more tailored where AI could kind of help you do it? And this process takes a long time, because a lot of times these are hand-drawn or, you know, automated to some extent, but more or less hand-drawn. Every time you go through the loop, the airplane gets smarter. So if you could do that, you know, computer fast, you'd end up with something that was better at the end. Okay, I'm going to go quickly now. This is a chart that's been around for years. I think the guy that drew it in the 50s, where it says, here's what happens if you let a given airplane. You get something that isn't going to work. You can look at all those configurations and say, none of these are going to be a great airplane. So I'm going to quickly hit over that. Okay, so I'm going to start building a new airplane. What do I want to do? Why do I do it? My J3 Cub still flies. It's great. It's 80 years old, and I love it. Well, the thing is that things move along. Your J3 Cub can't take a jet engine with afterburning and all that in there. And so the whole time is going on, things are improving. Engine technology is getting better. You've got higher thrust to weight ratios. They're more efficient. Jet fighters typically now have turbo fans on them. The fans are small, but nonetheless, they've got fans on them. So you get more thrust. All these things are good. Advanced structures, high strength to weight ratio, corrosion resistant, all that plays into it. Power electronics, this kind of changed. I worked in the electrical power system, and these power electronics have changed everything in the way we do stuff. F-35 has electric start, so the same generator that's used for the generation also starts the aircraft. So it's kind of a twofer. You can leave a part at home because you don't need a starter or air turbine starter or whatever. You can just use the generator to do both purposes. Computers is huge. Back when the F-16 was first designed, there really weren't digital computers that were fast. They were all relatively slow. And so F-16 actually was built with a negative static margin. It was unstable. And so they needed something to stabilize it, so they used a flight control computer. That flight control computer was actually analog. They did it with op amps and that kind of thing. I can't remember what block they switched over to digital. It's digital now. But back in the day, it was just op amps and generators, differentiators and capacitors and resistors. It wasn't, some super high tech, very, very fast microprocessor. So when you put all this stuff together, you get this general over here, and he's smiling because he's got his new airplane he's really excited about to fly. Okay, now let's build one. We're going to set a set of requirements, and we're going to see what that might look like when we do an airplane. So let's say our max speed, we're going to do Mach 0.8. Just made it up. These are from nothing. It's just kind of thinking about stuff. So what that's going to do is it's going to impact the wing design. I'm not going to put glider wings on it that go out, hundreds of feet. It's going to have to be pretty tight, that kind of thing. I'm going to put the service ceiling at 50,000 feet. The reason I picked that was because that's where you can start seeing the curvature there pretty clearly. And I thought, hey, if I was a pilot, I'd like to see that. So that's kind of fun. But the deal is that you're going to have to pressurize the cockpit, because at that particular point, you probably don't need a pressure suit, but you're definitely going to need to pressurize the cabin to keep the pilot from having issues with hypoxia and those kind of things. And keep in mind, at 50,000 feet, water boils at 103 degrees. You know, when you look at the back of the cake mix box, it tells you if you're making it in Denver, you got to cook it longer. That's because water boils at a lower temperature, so it takes longer to cook. Now, if you go up to like 60,000 feet, you're going to need a pressure suit, because at that point, if you lose pressure in the cabin, you can actually start running into problems with stuff in your bloodstream coming out of solution, water boiling, all that kind of stuff. That's why he wouldn't have got the opportunity to walk in the cafe in the next scene. Also, the fuel tanks, you're going to have to slightly pressurize those, because again, stuff boils at a pretty low temperature up there, and if you've got fuel in your tanks, it gets really hot from the sun beating down on it. We're just going to say off the cuff, we're going to make it single seat. And so if you do that, now you've got it really impacts how you're going to train your pilots. You can't have a guy in back to bail you out if there's a problem. You're going to have simulators. You know, all this stuff is going to have to play into it, because the first time the guy's going to see the jet is when he's actually flying it. Takeoff distances is huge. There's some airplanes that are really, really large, like C-17. It actually has an unimproved strip requirement where they can, you know, dumpy gravel road, I guess. And I think it's got like a 2,000-foot takeoff roll under some circumstances. So it's a huge airplane, but it's got those high flotation requirements. And then it said fun to fly. So that's basically, I want the handling qualities to be sweet, where it's going to be, you move the stick and the airplane hops for you. Okay, just real quickly, this is something I kind of just sketched up that I thought would kind of ish meet these requirements. Slightly swept wing that helps you, like the transonic, the 0.8 Mach number region. Here's your fuel tanks. I kind of showed where I put those in. I left a little hole for an actuator for the flap and the aileron. There's a couple of fuel tanks in the fuselage. Here they are. Here the tanks are in the side view. And then if you go into the sections, you can kind of see that there's going to be an inlet, which is right here. The air is going to come in, kind of bend around the corner, and then it's going to get support. Sketched in some routing tunnels, because if you think about it, you want redundancy in your subsystems, and so if you have multiple channels of a thing, you don't want to route them down the same tunnel in the airplane, because then if something bad happens, like an engine throws a turbine blade, or a bird hits you and pokes through the airplane, you don't want that one piece of damage to take out multiple systems. So the green is kind of like where the routing tunnels would be. Here you can kind of see the fuel be out in the wings and kind of over the top. I made 2 tanks here because if you notice, you can see the lines coming up. The reason for that is if you made that 1 tank, you'd have to put 2 drains in it, or you trap fuel in one side. So you got to kind of think about how it's going to lay out. In the back here, this red thing is the engine. You can see the fuel over the top, and again, 3 routing tunnels, and there's just some boxes that are kind of stuffed in there. One thing I wanted to kind of detail is the CG stuff. This is actually the fuel CG. I calculated the mass of these various tanks and figured out where the CG would be, and it's right here. This neutral point was based on a program that I ran that's probably not very accurate, but it just kind of gives you an idea. So I wanted to set a CG limit that was just slightly forward to that, again, because I'm trying to make it marginally stable so it's really fun to fly. And then there's an upper limit that would be set by the aerodynamics guys when they look at landing and high alpha to make sure that the airplane was always going to be stable. One of the things, a couple of examples are really important. Like if you look at this is called the design eye of the airplane, where you can look and see how far down the pilot's going to be able to see. And you see this is 11 degrees. That's terrible. You wouldn't really want that in an airplane, so that'd have to get fixed. This is called a tip-back angle, where when the airplane's rotating, it's got to get to like its max coefficient of lift in order to fly off the ground. So here it's shown as 12 degrees. That's kind of marginal. You could probably make that work, but it's going to be kind of sketchy. Another would go back to the design eye in this section. You see there's a 26-degree down angle. Again, that's awful. The pilot would feel like he's sitting in the middle of a bathtub. He wouldn't be able to see very much. So there's a couple things in there that are bad. But this is just to kind of give you an idea what a preliminary design type thing might look like. Okay, for a fuel CG, I'm going to go over this really quickly. Here what's going to happen is you're going to figure out what tanks you want to burn first. So in this particular case, this plot is showing the weight of the aircraft. This is showing the CG location in inches. So the CG with everything full is going to be at this point. And then what happens is you're going to burn a tank down so that the weight of the airplane is going to come down and it's going to affect the CG. So I decided I was going to burn the wing tanks first in order to minimize the inertia in the roll axis, which is typically what aircraft will do. Then you burn one of the tanks in the forward fuselage. Now notice when we burn that tank, the CG goes to a bad spot. We're going in front of the forward limit. So we'd have to do something about that. Then as you continue to burn the last tank, you get down here to the empty weight where the CG gets back. Again, it's inside the envelope. But that's not going to work. You're going to have to do something. Redesign the tanks, make a more complex system, break them up into smaller pieces or something like that. So this is kind of design review. Again, we already talked about a lot of these things. In this review, they tell you, hey, pilot, the CG's wrong, it needs to be fixed. The positives of this, the neutral point and the CG are pretty close, so it's probably going to be fun to fly. And then for future actions, hey, you need more detail about how your subsystems are going to work and where your landing gear is going to go. Okay, so now man versus God. We're getting back to where we started. Man's designs, brute force. I mean, everything is hard. It's structures are rigid, nothing moves. There's tight margins for control. The CG's got to be this close to the neutral point. All these things are hard to do. Now the thing is about it though, when you think about it, it's complicated on the surface, but when you look at the details, like your hand out the window or the arrow going forward, it's all really simple. There's nothing super great there. Now when you look at God's designs, it's finesse, there's flexibility. One thing that I've always been impressed with is a bird's wing and how incredibly adaptive it is. It can change the camber, it can change the sweep, it can move it forward or backward, it can change the key rule. So depending on what condition the bird is seeing, it can basically adjust its geometry to suit it. And it's incredibly smart. It's flown for years and knows how to do it. So with the bird, though, you look at one and you go, that's easy. Look, there he is. He's making it easy. But when you look at the details, the feathers, the muscles, the bones are hollow. All these things are incredibly complicated in the details. Okay, here's my cheat sheet on a comparison between birds and man. So you think of manufacturing. Where does this thing come from? So with man, they've got assembly buildings. There's an incredibly large supply chain, highly skilled workforce, all these guys popping rivets and doing all this good stuff. With the bird, you got an egg and a nest. Okay, flight controls. Again, these are fairly close actually. Flight controls, typically, small airplanes just going to have a guy that's flying it. Some more complicated airplanes that have computers that help you out. Stuff's connected with cables and wires, and you want to put the CG in front of the neutral point for stability. Birds, same kind of thing, brains, nerves, except for this highly dynamic wing design where they can change all these things to adapt to the conditions that they see. Flight training. To get your pilot's license, you've got to be more than 17 years old. You have to have 20 hours with an instructor, 40 hours total time. You've got to pass an FAA exam and a check ride. With the bird, in 7 to 100 days, the mom kicks them out of the nest and they fly. So the small bird, 7 days, which to me, God, that's incredibly short. Sensing, airplanes use gyros, accelerometers, compasses, all these things. Birds, they use their eyes, their ears, and they can sense magnetic fields, at least the ones that migrate do. Propulsion, man stuff, incredibly loud. You've got piston engines, jet engines, all this stuff. They're just loud and awful. Birds, they use muscles and wings, pretty quiet. You don't mind the birds flying over your head, whereas an F-35, not so much. Landing surfaces, airplanes, 12,000 feet, long runways, 2,000 feet for a grass field maybe. Birds, they can land on a wire, a tree branch, Walmart sign, you name it, they can land on it. Maintenance. This is huge because a lot of times you don't think about maintenance of an airplane, but there's inspections that have to happen. Components have to be replaced. You have to have access panels, all these things. Well, God took care of it. Birds can heal themselves, at least to a point. Power sources, aircraft require like really, really refined jet fuel, all these kind of things. Can't have particulates in it. And birds just kind of eat whatever, bugs, nuts, fruit. I guess worms, I left them off. Sorry, worms. Okay, last slide, getting off the stage here. When you think about what's going on here, an eagle grabbing a fish, you look at a video of it, you go, oh, okay, that's interesting. But there's a tracking task that the eyes are doing. They're keeping track of the thing. They're figuring out what flight path I need to do to intercept this fish. When I grab it, now I've got this huge change in my CG because this fish is heavy and I'm relatively light. Here's when you think about a hawk in a dive, and I thought this picture was great. I've never seen a picture this good of this happening. But you just look at that shape, and it's like, that is a perfect airfoil. The Wright brothers would love to have that one. And I thought this was kind of interesting too, that as this bird's flying along, you see these feathers are popping up. It's kind of like a little bit of a speed brake. It keeps that thing from flying too fast, because if it gets too fast, you may have trouble with control or pulling out, that kind of thing. If a bird's flying in high wind days, you might see them really crank up the hedral on their wings because they want to be more stable. And then if they're just doing endurance where they're looking for mice or whatever in the field, it's not too windy a day, you'll see them flatten out their wings and kind of use the tips for control, for roll control and that kind of thing. So again, this is how God does it. And it's not brute force. It's beautiful, and you just can't beat it. God is great.
Thank you. Thank you, Tom. Very, very, very good presentation.
Thank you.
So we'll open it up to questions for a little while.
Yeah, I'm sorry for going a little bit long. Sometimes I get chatty.
Hey, Tom?
Yeah.
So, we saw an owl flying through the woods, doing all kinds of crazy maneuvers.
Yep.
It never made a sound.
Yeah.
How does that work?
They, the wings and the feathers and all that are designed to, in my opinion, I mean, I don't have access to God, but a lot of those things make them fly incredibly quietly, because you'll get like small vortices that'll keep flow attached when on a real airplane it might separate. Feather design is amazing. I mean, I bet there's people that have done dissertations on that. It's incredibly complex. I mean, we think about a feather design, the shaft is hollow. They used them for quills for years and years. And then they've got little intricate things that shoot off of there. All of them incredibly, incredibly complicated.
Owls are big birds.
Yeah.
They maneuver like that.
Yeah.
It's kind of startling.
Now, we have some turkeys that hang around our house. And one day I got the opportunity to hear one of the turkeys take off and fly up and land on our roof. And I said in the pitch that they're quiet, but when you got a turkey that probably weighs 15 pounds that's trying to take off and land on your roof, he does make some noise.
I don't watch YouTube at all, but there is a video of that very subject on YouTube where they talk about the sound that small birds make with the high flutter. And then I think it's the barn owl, but one of the owls, he's got such a large wing with one swoop, he just glides. And and it doesn't make any noise because he's not fluttering.
Right.
Right.
Well, when you watch birds fly, there's different techniques. There's what I call LBBs, little brown birds. I don't know what they are, but they'll flap for a little bit, and then they'll stop, and they'll put their wings down to their side, minimizing their surface area, and they'll start falling. And then as they get to a certain point where they're not comfortable anymore, they'll get their wings back out, flap, get altitude again, and then they'll just repeat that over and over and over. And it's, when you think about it, it's like, oh, okay, they're reducing their surface area, but they're keeping their momentum. And, it's just like genius.
Mm-hmm.
But, yeah.
Andy?
Oh, sorry.
I remember reading about the Wright brothers. David McCullough wrote about them.
Mm-hmm.
And I was just so impressed by their methodology, because they documented everything. They kept all the details so they could go back and look and see what had happened. And it just speaks to the value of that kind of detail.
Yeah.
And what you can learn from it, and how, I just pray that people are being taught to take that kind of care in managing those those details.
And the discipline it took to
Yes.
do that. And it's interesting with the Wright brothers because a lot of the aerodynamic data that was out there when they started was wrong. And so they had to kind of realize, hey, this is just not right. And then that takes courage in and of itself. Because here you've got this body of knowledge and you're saying, big X, it's wrong, we're moving on. And then they did it themselves.
Yeah, we have a question over here. Yes, sir.
Same book, they talk about how they studied the birds. The Wright brothers studied the birds.
Mhm.
And then from the straight flight, and they had to study them how they turned.
Yeah. Yeah, the wing warping, I mean, that can be a topic of its just in and of itself. Because it's incredible how that works. I didn't even understand it until I went to Dayton and saw the Wright Flyer. And you're looking at it and you're like, oh my goodness, now I get it. I never understood it before. Because they say wing warping, but you're like, well, how does it work? But it's crazy. They did it outstanding.
In that book, they also said that the difference between the Wright brothers and everybody else was when he began to study birds for that reason.
Mhm.
That was the whole turning point for him.
Yeah. And when they focused on stability instead of power, because like Langley and a lot of other guys were saying, hey, we want a huge engine. And it's like, they were kind of like, I think we can do it with 12 horsepower. You know, one thing I want to show you that's kind of interesting, I was showing this, whoops, too far. When you look at the Wright brothers airplane, I was pointing this out to David earlier, they were very concerned about stability. So these two props rotate. So if you try to turn or move them in any way, you're going to feel a torque, just like on a bicycle wheel. So the Wright brothers were concerned about that because they didn't want to fight that. And so what they ended up doing was they've got their motor sitting here, and you can see this chain actually goes up and over and comes back around, kind of in a figure 8 type arrangement. This one goes out, just comes straight around and back to the motor. So one of the chains is twisted and one of them's not. And the reason they did that was they wanted counter-rotating props, so the torque from the propellers would cancel, and they wouldn't have to worry about that force. So I mean, genius, absolute genius.
One more question over here.
Ornithology is a fascinating subject, and birds of prey especially have always been interested in. But I'm also interested in hummingbirds, and from an engineering perspective, would that be more brutish than flexibility? Because they do not glide. Their wings are constantly in motion.
That is true.
Yeah.
That is true. And that's probably a time where it was God just showing off.
And same thing with the bumblebee.
Yeah,
Engineers for
yeah. Same thing. Well,
decades have said it can't fly, and yet it does.
there was a guy I knew that flew helicopters, and his favorite saying was that a helicopter doesn't fly, it beats the air into submission. So it's kind of like hummingbirds. They just kind of beat it into submission.
All right. Thank you, Tom.